the jet flames, laminar jet diffusion flames. So, we obtained this equation for the flame length using the constant density solution. So, we discussed this this morning. Okay. Then Burke-Schumann solution for Burke-Schumann flame. So, this you can refer to every textbook, almost every textbook has this solution. Okay. And the flame length will have those similar parameters in the other solution also, obviously. Now, these Roper correlations, they are used in engineering practice. So we'll discuss a little more about the Roper correlations and how do we control the flame length using these kind of correlations. Okay. So now, if you compare with the simple solution, okay, so you still have QF. Okay, then use the diffusivity, mass diffusivity, and then you have some temperature effect. Okay. So here, what is T infinity? That's the ambient temperature. Okay, and that's the fuel temperature. So generally, this ratio will be about 1, but it accommodates the variation in fuel temperature, ambient temperature, and this is the flame temperature. Okay. So this brings indirectly the buoyancy effect. Okay. And then you have this factor S, so it's the natural log of 1 plus 1 over S, which is actually similar to this YFS. Okay. So we can take some example. We had calculated YFS earlier. So YFS was 0.055 for methane and about half for hydrogen, right? Now, what is S? So simplest way is the moles of air divided by the moles of fuel. So air fuel ratio, okay, by mole, by volume. So S is now corresponding to these two cases. Okay. So for methane case, what is this ratio? So moles of air. So 2 times 4.76, right, moles of air. Okay. And what about moles of fuel? That's 1. Okay. So this value is 9.52. Whereas for hydrogen, okay, it's 1/2 mole of oxygen, and then that many moles of air, right? So that's 2.38. Okay. So now let's calculate that factor. Okay. Log of 1 plus 1 over S. Okay. So basically the stoichiometric, a stoichiometry, is reflected through this equation. Okay. So if you do for methane, so what do we get? Log of 1 plus 1 over 9.52. So what will be this value? So we have two cases, methane and hydrogen. So let's write the values for these. So, this is about 0.1, 1.1, which should be about 0.1. No, it should be not about 0.1. Log 0.09. Okay. And for hydrogen, one plus 1 over 2.38. Okay. So, this is higher for hydrogen. Okay. Moles of air, yeah. And of course, the justification of using this log of 1 plus 1 over S is that this correlates well with the experimental data. Okay. You find that the stoichiometry expressed through this S. Okay. So, remember S is air moles, number of moles of air divided by. Okay. Later on, I will show that there is another definition for S which is very similar to this. Okay. But the point is that it goes with the stoichiometry. Okay. All right. Yeah, that's for the circular. Yeah, well, I'm going to actually, that's a very timely question. I'm going to discuss for other jets, rectangular jets, okay, or square jets. That's what you are asking, right?
I am asking like first solution, that is constant density solution, is valid for circular port.
Yeah, it was done for the circular port. Yeah. So, we will have more material to discuss the effect of S. So, first now we will discuss this correlation for square port and slot burners. So, square port and the rectangular ports. Okay. So, this is taken from Turn's book. So, it plots the flame length versus the volume flow rate. Okay. So, if you look at this equation for the circular ports, this is all circular ports, it is linearly proportional to QF. Okay. So, for circular port, it has a linear variation, the flame length versus flow rate. Okay. And then they have for other shapes. So, slot burner, slot burner. So, slot burner means you have like a rectangular burner, rectangular jet like this. Okay. So, this is H, the distance between the plates, that is B. Okay. So, then H over B is important. Okay. So, you can see that if you decrease this B, then the flame length will reduce. Okay. So, you can see that effect here when you increase H over B, you increase H over B. So, you are either by increasing B decreasing B or increasing H, and the flame height can be decreased. Okay. And then of course, the opposite effect as you increase H over B. Okay. So, for square port, H over B will be equal to 1, square jets. Okay. So, then the flame length will be higher. And in the Turn's book, there are equations also, correlations for square jets and rectangular jets. If you want to look at those equations, the correlations. Okay, now look at the effect of various other parameters. So, the nozzle shape, effect of flow rate that we know already. Now, we can also look at dimensionally, but just from a physical point of view. If you look at the original equation, okay, so we had done this before. LF divided by VE, okay, is proportional to R square over D, right? Okay. So now, what we are getting is that LF increases, for example, as you increase R. Okay. So physically, you can explain this, using this relationship. Okay. When you are increasing R, okay, and keeping the other parameters fixed, okay. So what happens to this? Okay. And what is that? That's the diffusion time. So increasing time, increasing R, you are increasing the diffusion time. Okay. So this time has to follow the diffusion time. So that means this time has to be increased also. So if you don't change velocity, that means the flame length will increase. Okay. So same way you can explain, what is the effect of, VE. Because if you change VE, then you are changing the flow time or the convection time. Okay. But this time is not changed, so you cannot change the convection time independently. Okay. So if you increase VE, then LF has to increase also to satisfy the constraint by the diffusion time. So just using the time scales, you can explain, the variation, why should physically, change, why should LF change with, V, R, and also the diffusivity. Okay. Because if you change diffusivity, again you are changing this time, so this time has to change, okay, because the convection balances the diffusion part. Okay. So now we already discussed the effect of the nozzle shape, circular jets, square jets, slot jets, or rectangular jets. So important observation here is that the flame length decreases as the aspect ratio increases. Okay. Okay, next is now S. Okay, we just discussed two examples for S. Okay. So for any given fuel, you can calculate the value of S. How would you calculate the value of S? Just using the stoichiometry equation, right? Okay, take 1 mole of fuel and then calculate how many moles of air. Okay. So what you see from here is if the effect of fuel. Okay. So methane, if you calculate, so this is just a value, right? X plus y over 4. Okay. So this value is, you have to multiply by 4.76. Remember that? Okay. This a value represents the moles of oxygen. Okay. So every 1 mole of oxygen corresponds to 4.76 moles. But if you change the amount of oxygen in air, then that 4.6 will also change. Okay. So let's say, for example, if 20% oxygen instead of 21%, okay, then the 4.76 will become 5. 1 mole of oxygen and then 4 moles of nitrogen. Okay. Then S value will also change. Okay. So this also, we can also discuss the effect of changing the mole fraction of oxygen in air on the flame height or flame length. So all you have to do is, here instead of 1, instead of 1, you say that's the mole fraction of oxygen. So for standard conditions, this will be, what will be the value? 0.21, okay, which gives a factor of 4.76. Okay. So S otherwise is 4.76 times this value. right? Okay. Because for methane it is 2, then you multiply by 4.76, or you can just take 1 over the mole fraction of oxygen. Okay. So, 1 over x over 2 represents number of moles of air, okay, per mole of oxygen. Okay. So, anyway, so this is the effect of the fuel. As you go to larger hydrocarbons, okay, the number of moles of oxygen is increased, right, and so the number of moles of air is increased. Okay. And you can see that as S increases, 1 over S, this factor will decrease. Okay. So, this 1 plus 1 over S goes close to 1. Okay. And log of 1 is 0, close to 0. Okay. So, as S increases, this flame length will increase, okay, because this 1 plus 1 over S decreases. Okay. So, this new denominator decreases with S, so flame length will increase. Okay. And so, this is the plot again from Turn's book: methane, ethane, propane, and last one is heptane, I guess. No, here it's butane. Okay. I just wrote also for heptane here. Any questions?
Sir, any backslide?
Yeah. Okay, go ahead.
Given formula on back. Yes, sir, actually this LF experimental T AD upon T flame or T fuel?
No, this is correct. What has been done here, okay, I think they use some flame temperature value and the diffusivity value. It's the same expression kind of. Okay. So, yeah, I will double check, but I am pretty sure this is correct. They use some adiabatic flame temperature. So, that is why this factor appears. Okay. Anything else?
So for different species, the adiabatic temperature is different.
That's true.
But
Yeah.
in S, if they have used any particular species, then S value.
Yeah, you are right. Yeah. Okay. Yeah, I'll double check whether this is, because whether this factor is included or this factor. Yeah, I don't remember offhand now. Okay, it's in the Turn's book, so we'll check. Okay. So, this is the effect of stoichiometry, and also in air, okay, if you increase a diluent, you can decrease the mole fraction of oxygen, okay, then the flame length also increases, okay, because then you are changing the stoichiometry. Okay. Okay, this is a very interesting effect. Okay. You can also change the flame length by adding air to the fuel jet. Okay. So, this equation includes that effect. Okay. So, the addition of air decreases the flame length. Now, how much air is added is expressed through this equation. So, let us look at this equation a little bit more. Okay, so S pure is the original value of S. Okay. S pure means no air is added to the fuel jet. Okay. And now, if you added some air, then amount of air addition phi, okay, phi is expressed as in terms of the percentage of air added. Okay. So, basically if you take 10% of air from air, okay, and add it to the fuel jet, okay, that will change the value of S according to that equation. So, for example, if I take in this table here I given 0.25, okay. So, if I use phi equal to 0.25, this will be 0.25, okay. So, if you take the ratio here, okay, so LFO, that is a flame length without adding air to the fuel jet. Okay. So, if I take the ratio LF divided by LFO, okay. So, now LF depends as log of 1 plus 1 over S, correct? Question? Yeah. Yeah, I'll come to that in a minute. So, without any air addition, okay, this is the expression, right? So, with air addition we change this S, so this we call S pure without air addition. Okay. So, with air addition to the fuel jet, we have new expression for this. So, this is the with air addition to the fuel jet. Okay. So, if you take the ratio, you get this equation. Okay. So, now we can see the effect of adding air to the fuel jet. So, if this is phi value is 0.25, then what is the value of S? Okay. 1 minus 0.25 divided by S pure, and let us take methane case. Okay. So, I do not know whether there is a typo. Let me just double check in the book. Okay. Okay, let us write this equation and then I will look into it. Yeah. Sorry? Flame temperature, yeah. Yeah.
So when we are increasing the percentage in the combustion area, so wouldn't that be affecting the temperature?
Change the flame temperature,
So
yeah,
how do we show
yeah.
that this ratio is due to not, that's not due to the temperature change, and that's purely dependent upon the S.
No, that has been shown, they have verified it experimentally. Okay, when you, okay. There are ways you can add, then also you can keep the flame temperature same, okay, but you can still change the flame length. Yeah, okay. Because more based on the stoichiometry than the flame temperature. Okay. Your flame temperature will have a secondary effect also. Okay, let's write down this expression so then we can double check what's wrong with that. I had it on the PowerPoint. Okay. Where phi here is defined as the fraction of the stoichiometry requirement. Okay. Okay, so that there was a typo here, right? Anybody write down that expression because I cannot see both of them. What was in the book?
1 minus
Just 1 minus psi. So actually, so there is no S pure here, is just 1 minus psi. Okay. This is correct, and there is no S pure here, right? Okay. Yeah, okay. So, can make that correction. So, remove this S pure from the here, from the numerator, and from here. So, this is just, okay, the psi. Okay. So, in that case, the new value of S here will be just 1 minus 0.25 divided by, so then S pure comes here, so we can divide by S pure. Okay. No, we can't do this. So, this is 1 over S pure plus 0.25. Okay. So, what do we get for this S? Do we get what I have it here? So, let us assume this is methane. So, then S pure, what was the value? 9. You remember that value for methane for S? 9.52. Yeah, this is the right one. Okay. So, if you use for methane, so what do we get here? 0.75. Okay. 1 over 9.52 plus 0.25. Do we get this value then?
2.1.
So, that's the, then, yeah, so this equation is wrong, but these values are correct. Okay. So, it's just a typo. So, by adding air to the fuel jet, what is the result? Okay. We decrease the value of S. Okay. Because you can also see physically, but we decrease the value of S. So, as S decreases, the flame length also decreases. Okay. This is just mathematically looking at this expression, because we are decreasing the value of S. Okay. Now, physically also it makes sense. Now, okay, when you add air, what happens to the stoichiometry? Okay. Stoichiometry value increases. Okay. So, the fuel, you start with the fuel jet at x equal to 0. Okay. Where is the flame length? Where it reaches the stoichiometry value. Okay. So, if you increase that value, YFS value will increase now. Okay. So, it does not have to go to 0.055. Okay. The flame will be where now it will be more than 0.55. Okay. 0.055. So, you are changing the stoichiometry by adding, now if you add more air, so instead of 25%, so this is 25% compared to the no air case. Okay. So, as a percentage of the stoichiometric requirements. So, if you add 40% of air, okay, as a percentage of the stoichiometric value, then the flame length is decreased by a factor of 0.16. Okay. 0.5, 0.13. Now, eventually what happens is, as you keep adding more air, what will be the limit? Remember, you are adding air to the fuel jet. Okay. So, let us also calculate, okay, what is the equivalence ratio for these cases. Okay. So, let us calculate equivalence ratio for the pure case. Of course, it is 1, right, because there is no equivalence ratio is infinity for the pure case. So, as pure case, phi is infinity because there is no air in the fuel. Okay. So, now let us say for, okay, let us do for 0.4. So, when psi is 0.4, okay. So, now what there is a, okay. I think I have these values. So, let us not, I think we will be spending a lot of time, calculating. Okay. Because you need to calculate how many moles of air we are adding. Okay. Yeah, maybe we can do this way. So, 0.4 of stoichiometry. Okay. So, now for methane, these are the number of moles of air, right. So, now if you take 0.4 of this, so add it to the fuel, okay. So, your fuel 0.4 times 9.52. So, what is the equivalence ratio for this case now? Now, we can calculate the equivalence ratio. I am not 100% sure whether this is exactly correct, okay, but more or less is correct, but I will double check, okay, after the session. So, what will be the equivalence ratio? Because for phi equal to 1, it is 9.52, right. Now, equivalence ratio when it is 1, then the amount of air is, okay. So, now what is the value? What is F over A now? (16) divided by 0.4 times 9.52 times 28.9, right? Okay. And the stoichiometric value is for phi stoichiometric. So, again it is 16, 9.52, 28.9. Okay. So, it is roughly 0.4, which is 2.5. Okay. So, by adding 40% of the stoichiometric requirement, okay, adding that much air in the fuel, okay, now the equivalence ratio becomes 2.5. Okay. So, you see, then you have what you call partially premixed flames. The equivalence ratio of the fuel jet now is not infinity, it is 2.5. Okay. So, if you add lot more air, the equivalence ratio will become 1. If you keep adding more, so when it is equivalence ratio is one kind of flame we have. Okay. Yeah. It becomes premixed flame. So, you only add certain amount of air to the fuel jet. Okay. As you add more, first it will become partially premixed. So, equivalence ratio go 10, 5. Once it becomes 5, 10, actually those are partially premixed flames. And if you go near than 4, 3, then you get double flames. Okay. You also get premixed flames. So, you don't want to go to the Bunsen burner flame are actually 2 flames. Okay. So, if you have, like I can look in my kitchen, there is the Bunsen burner frame, there is a premixed flame in the middle, small premixed flames, and then you have the diffusion flame. Okay.
Sir, which one is more efficient, like premixed flame or partially premixed flame? In terms of efficiency of the combustion.
Or the complete combustion, you mean? Okay.
Which one is more efficient? If you're using like premixed.
Well, it's not just efficiency. Most of these burners, okay, like kitchen burner, those are partially premixed flames because you want the flame height to be very small. Okay. So the efficiency is about same. I think in both you will burn the fuel. Okay. But the length becomes very small.
So means partially premixing you are doing to reduce the combustion length, right?
Yeah, exactly. Yeah.
The combustion length.
For jet flames. Okay. So, what is the net observation takeaway? That as you start increasing, adding air to the fuel jet, the flame length decreases, and then at some value of air, amount of air, you get this double flame, partially premixed flames. Okay. So, I have a graph here. Well, let's look at the first graph. Okay. So, this is what we are just talking about. This is the percentage of primary aeration means amount of added to the fuel jet. So, 20%, 40%. Okay. So, according to this, okay, when you add 60%, you reach the rich limit. Rich limit means you get 2 flames, but that is a rough result. We have observed 2 flames even less than this value. Okay, even at 40%, you can get 2 flames. Okay, and this graph shows changing the amount of oxygen in air. Okay. So, if you add more oxygen or you have less nitrogen, then also you can decrease the flame length. So, oxygenated flames will have shorter flame length. Okay. And this you can explain by using this equation. Okay. So, if you have more oxygen, S value will decrease, and that will also decrease the flame length. So, remember this is a correlation, it is not like exact equation, okay, but it gives the effect of these parameters. So, when you look at this material, you should also look at okay, how physically does it make sense. Okay. So, this is the effect of, so let me go back here. So, as you increase that, if you decrease on the other hand, flame becomes longer and longer. Okay. Because again the flame shape is determined by the stoichiometric conditions. Okay. So, the stoichiometric conditions are modified when you decrease the amount of oxygen in air or increase, when you change the amount of oxygen. These are pictures of actual experiments, okay, which were done in our lab, like several years back, but I think 15 years back. Okay. So, this is exactly what we are talking about. Okay, we are not even at primary air 40%, but because for 40% the phi value was about 2.5. So this is more than 40% a little bit. Okay. And you see the premix flame appearing in these flames. Okay. For propane air, this tip is open because of this non-unity Lewis number effect. Okay. The Lewis number is less than 1. Okay. Otherwise, the overall behavior is very similar. So you get double flame, and as you add more air, phi value decreases, right? This is the value of phi where in the fuel jet. Okay. So when you do experiment, you have like 2 tubes, one is bringing fuel and one is bringing air, and you control the flow rates in order to control the equivalence ratio. Okay. So what you see is that as you keep decreasing phi, then most of the burning is taking place in the premix flame. Okay. Relatively much less burning in the diffusion flame. So eventually diffusion flame kind of disappears. Okay. So this is not what you want to do in the home burners. You want to operate somewhere here, okay? Maybe somewhere here in this range. Okay. According to this graph, it says 60% aeration. For 60%, I think the equivalence ratio will be probably about 1.6, 1.7. Okay. So, some value, less than 60%. And then we discuss this. And the last one is, okay, you can also add diluent. Okay. So let's say if you add 10% diluent, okay, to the fuel stream. Okay, so what happens to the YF value at at x equal to 0? If you add 10% diluent, let's say nitrogen, to the fuel stream. Okay, so what is the value of YF? Okay, let's say 10% by mass. So then it becomes already 0.99, right? Okay, let's say 50%. So it's already 0.5. So now you have to decrease your YF value from 0.5 to the stoichiometric value. Okay. So physically you can see that the flame height will decrease, okay, by adding diluent to the fuel stream. Okay. So that's another way, practical way of you add some diluent, okay, in the fuel stream, that will decrease the flame length. Okay. And you can include that effect, by, in the equation for S. Okay. Because basically it goes in the numerator, which becomes 1 minus x dilution. Okay. And this is in terms of percentage. Okay, 0.1, 0.2, 0.3, whatever value. Okay, diluent effect is not shown in this any of these graphs. Okay. Okay, now the rest of the session, okay, I will show some results for counterflow flame, okay, and some numerical results for the jet flame. Okay, now counterflow flames, okay, if you use Chemkin or some other software like Antera, okay, then you start with the governing equations for cylindrical coordinates, again, R and X, okay, but then you can reduce them to ordinary differential equation by using some, mathematical, okay, manipulations. So I'll show you those equations so those are for 1D calculations. So because now you are doing just solving one-dimensional equations. So those are ordinary differential equations. Okay. Then, okay, recently a lot of calculations have been done using full 2D case, okay, for counterflow flame. So I'll just show you results for both. Okay. So this is a Word document. So let's see if it shows clearly. So in the advanced combustion course, I give this as an exercise that they have to derive the equations for the counterflow flame. So you start with your, so everybody can see these equations, right? Okay. So this is your continuity equation, okay. And then using some transformation and manipulation, you can change it to one-dimensional form. So here you see equation 3.17. Okay. If somebody wants, I can send this document. 3.17. So now everything is only a function of x. Okay. So the axial momentum equation now. Okay, there is only dependence on x. Okay. Similarly, you can change the radial momentum equation. Okay. So this becomes like the radial momentum equation. Okay. And now the species equation. Okay. So species equation for any species k, okay, becomes like this. You see now it's a ordinary differential equation. Otherwise, the same equation which we have discussed 2-3 times. Okay. This is the convection part. Okay. U is not exactly the velocity, it's it includes velocity, and this is the diffusion part, and that's the reaction part. Okay. Then we have the energy equation. So the energy equation again start with the Schwab-Zeldovich, take steady state, okay, and then write it for cylindrical coordinates. Okay. And then some steps involved, to again get it to the ordinary differential equation. Okay. So Chemkin or other softwares, they solve these equations, one-dimensional equations. Okay. But you can use detailed chemistry now. Okay. You can look at whatever properties, the flame structure. You can look at emissions. If you have the NOx chemistry in your model, if you have soot chemistry, you can also include soot. And then, of course, the boundary conditions and all that. So these are the equations used. Of course, numerical, part of this equation. So numerically, you get the finite difference form, and then you solve. So that's what is done in Chemkin. Okay. And again, you supply the other 3 files, the thermo file, kinetic file, and the transport file. Okay. So there are a lot of results have been obtained using. Okay. For 2-dimensional flames, I showed you the equations yesterday. I'll show it. Okay, again quickly. So remember I discussed briefly these equations. Okay. So these are the same equations we discussed this morning. Also, some of these written in the instead of z now, instead of x, I'm using here Z. Okay. Otherwise, the same equation, the convection term, the diffusion term, and then the reaction term. Okay. Or viscous forces, pressure forces, depending on the whether it's the momentum equation or the species equation. Okay. And then again, we solve these equations on the computer with all those transport files. So this is not Chemkin when you use 2D results. Okay. So I'll show you some results quickly. What is the time? Okay, we have time. So these are very recent results. They are not very organized because we are still like writing these results. So this is using Chemkin, so one-dimensional simulation. Well, let me show you from a different paper. Okay, let's use this one. Okay. So this is from 2D calculations. Okay, this is syngas. So the syngas mixture is coming from the bottom. Okay. So this is the fuel jet where you get the syngas and the air oxidizer or air jet. So this is the OH and this is the temperature, and then you're showing the streamlines to indicate the flow. So you can see the stagnation plane, and the flame is very close to the stagnation plane here. Okay. So this is the flame structure from the 1D calculations. Okay. Now these flames are highly diluted flames. So in the fuel stream, you have hydrogen. So this is a syngas fuel, okay, but you have a lot of CO2. Okay. So there is a significant major amount of CO2. CO2 is like mole fraction is about 0.45. Okay. So the temperature. So we have to increase the initial temperature of the fuel stream to have a flame. At normal room temperature, you may not get any flame. Okay. And this is the typical flame structure again. So hydrogen, oxygen. Okay, the flame reaction zone is located here. Okay. And then the other results. Okay. So the temperature, this was almost like 900 degree here, more than 900. And then the adiabatic flame temperature is much lower, okay, because it's highly diluted with CO2. Okay. This we don't have to discuss right now, scalar dissipation rate. Okay, now this is interesting results. So if you compare the 1D and 2D results, for these cases they are almost identical. That means your 1D calculations are giving you quite good results, okay, because you are using the same transport, same chemistries, so same reaction mechanism. Okay. Only difference is one case it is 1D calculations, 1D equations. Other case it's 2D. Actually 2D unsteady. Okay. So of course for these cases it gives good results, both way, right? We have a lot more capabilities. Okay. Let's say you want to look at the soot emissions. Okay, maybe you need 2D. for those cases. Okay. Also, you can look at the extinction phenomena more closely using 2D results, 2D unsteady results. Okay. Because 1D steady results will just tell you, okay, you have flame, under certain conditions you don't have flame. It won't tell you how the flame extinguishes. Okay. So it will give you some overall picture, but not a lot of details. And then if you start looking at some radical species, then you see some differences between 1D and 2D. Okay. So what is the difference between 1D and 2D? Basically the transport. Okay. We are neglecting the variation in the radial direction for the 1D case. Okay. So 2D transport effects are, showing this is being reflected here in the OH. So you can see OH and H. Okay, there are differences, especially in the OH value. Then we look at the flame extinction using 2D results. Okay. So we now decrease the oxygen mole fraction in air. Okay, so 21%. Okay, this is how the flame looks like. Then you go to 10%. Okay, so you see the OH values are significantly reduced. You still have a flame, but this flame is now very close to extinction. You can see the temperature values are reduced. Here the temperature is about 1500, 1400. Here is, here the temperature was 950. Now in the flame it's more like 1200. Okay. So at 10% you are getting a stable flame, but it's close to extinction. I'll show you one more result. And then we'll stop. So this is more or less similar results. So at 10% you can see that OH, the radical species concentrations have become very small, and the flame is close to extinction. 7% flame is extinguished. Okay. So that's the minimum, okay, oxygen concentration for this particular flame. The last result I will show you here. Now this has capability to look at the transient extinction phenomena. Okay. Like we have a flame, how the flame will extinguish. Okay. So what the student did, so point, oh no, this is another one, next one. Oh, this one. Okay. So when the mole fraction of oxygen was 0.07, you get a flame very close to extinction. Okay. If you reduce the mole fraction of oxygen from 0.06 to 0.07 to 0.06, then the flame will extinguish. Okay. So we take a flame at 0.07, okay, and now we change the mole fraction of oxygen to 0.06. So since you are doing unsteady calculation, you can see what will happen to that flame. Okay. So that's the value of the unsteady calculation. Okay. So just look at the right hand side, OH mass fraction. Okay. So this is at 0 time, which corresponds to oxygen, okay, 7%, 0.07. Okay. Now we change the oxygen to 0.6. Okay. So after 1.75 millisecond, this is how the flame is. OH value is decreasing. Then this is after 1.875. So now what you see is the flame has extinguished near the center line. So the flame is first extinguishing near the center line, and then the entire flame extinguishes. So you can look at some other details of the phenomena which you cannot do with 1D steady calculation. Okay. You can also look at sometimes these flames start oscillating when they are close to extinction. So we can look at those oscillatory unsteady phenomena also. So I think I'll stop here.